Okay, so we have discussed inference and arguments in the context of propositional logic. At this point, we are ready to start discussing inference in the context of first order logic now. And the inference rules are not that different, but of course we have to be careful about the quantifiers now. Uh, the the important, the most important, let's say, inference rules when we are dealing with first order logic are the instantiation and generalization rules. And in fact, the instantiation rules are much more important. Um, if you have a universal quantified statement like for all x, p of x, this means uh, p of c for some c for any c in fact is true in this domain. Okay, uh, so here x is a variable. Okay, c here is a value in your domain. Okay, depends on what domain you have. Well, this statement is there's something wrong here. This should have been p of c for any c in the domain. They should have read p of c is true for any c in the domain. So that means if you have a universally quantified statement, and then if you plug in any value that is in your domain, what you get should be true. Okay, that is universal instantiation. And we also have the existential instantiation. This is a little bit more tricky. Now, if you have a existentially quantified statement, there exists x, p of x. So what does this tell us? This tells us that there is at least one x value that makes p of x true. But we do not know which x that is. That is the issue, okay? So here we represent this using what we call a Skolem constant, okay? Skolem comes from, if I remember correctly, a Norwegian mathematician. His last name is Skolem, and worked on these subjects. And this we call a Skolem constant, okay? Essentially, this is a naming procedure. K here is a constant that should not exist in other formulations. So you are actually giving a specific name for that x value, which makes p of x true, okay? The problem is we do not know, we may not know which x that satisfies p of x. Therefore, what we do is give a name to that. Okay, we do not know which one that is, but I'm going to call it K. So the key here is, of course, K, the name you use, shouldn't exist in your previous formulation. It should be a new name. Okay, it's like calling the 3.14, etc. That number, calling that pi. It's like that. Okay, so this is just a naming procedure, which we do not know exactly which x makes p of x true. There might even be multiple values, but since we know there is at least one, we call that k. That's called a Skolem constant. Okay, so existential instantiation is essentially giving a name to a value that satisfies p. Generalization is, I think, straightforward. In your domain, let's say you have C1, C2, etc., up to Cn, the values that x can take. Okay, if p can be satisfied for all of them, if p C1, p C2, p C3, etc., up to p Cn, if all of those are true, then we say that this is universal generalization. You can write for all x, p of x. So this essentially actually summarizes the relationship between propositional logic and first order logic. You see, first order logic is sort of a shorthand that we can express this entire statement in propositional logic, because we do not have quantifiers in propositional logic to express something is true for all possible values x can take. You have to write something like this in propositional logic because you do not have quantifiers there. Okay, so in this domain, if this is true, you can write for all x p of x, and that we call universal generalization. Similarly, we have existential generalization. Of course, if you have at least one C value in your domain that makes P of C true, then you can just write there exists an X that makes P of X true. Okay, we'll go to inference rules. Of course, we will talk about resolution, but before that, we would like to have some concepts that will help us define the procedure of resolution. And unification is one of them. And to define unification, we have to define what we call a substitution. A substitution is the replacement of a variable with a value or a term in the domain. Okay, so this is quite simple. We denote the substitution of variable x with value c with this notation x slash c. And here's a very simple example. Let's say we have this substitution x with Ali, and the propositional function we have is friend x, y. This simply says that wherever you see x, put Ali. Simple as that. So I have x here. This substitution will yield friend Ali y. Okay, so this is a more general statement. It just says x is friends with y. Okay, and if you make this substitution, what you do is you actually give a value to variable x, that is Ali. Okay, and this says that Ali is friends with y. Y here is still a variable. Okay, so it's still a general statement in that sense. Now this is called a substitution. So what is unification? Finding a substitution that makes two predicates identical is called unification. Okay, now let's say that you have friends x Mehmet. That means x is friends with Mehmet. And you also have this proposition function, friends Ali y. Okay, now these two predicates you can unify with this substitution. You see, I actually have two sets here, two substitution. Instead of x, put Ali, and instead of y, put Mehmet, in which case this will become friends Ali Mehmet, and this will become again friends Ali Mehmet, which are identical. Therefore, this substitution yields or makes these two identical, which we call unification. Okay, this will be important when we talk about resolution. Of course, not all predicates can be unified. For instance, friends x Mehmet and friends y Ali, we cannot unify because these are values, okay, and I cannot substitute them. Therefore, there is no substitution that will make these two identical. Therefore, I cannot unify these two. Of course, depending on the predicates, the unifier of them may or may not be unique. Here's an example. Friends x Mehmet and friends y z. Now you see you have two variables here, y and z. The substitution x into Ali, y into Ali, z into Mehmet works. Okay, it makes this friends Ali Mehmet and this friends Ali Mehmet. Or alternatively, this one, everything into Mehmet. This makes friends Mehmet Mehmet, and this also friends Mehmet Mehmet. Okay, so this is also a valid unifier. But this one, x into y and z into Mehmet. So x becomes a y, so this becomes friends y Mehmet, right? And z becomes Mehmet, so this is, both of them becomes friends y Mehmet. That's also a unifier. So you see, a unifier of two predicates may not be unique, okay? On the other hand, a unifier that places the fewest restrictions on the values of the variables, okay? In other words, it keeps them as general as possible, okay? So if you have a variable that you have to change, for instance, to unify these two, Z here has no alternative but to become Mehmet. Otherwise, you cannot unify them because this is a value. But X here is variable, Y here is variable. You can make them both into the same value. For instance, you can make them both Ali, you can make them both Ahmed, you can make them both W, I don't know. But if you do not specify them, they can stay variables, okay? So these two predicates let you to do that, okay? You don't have to assign values to X and Y. You can keep them variable. But Z, you have no choice because Mehmet is fixed here. So that we call the most general unifier. You keep your predicate as general as possible, and the unifier that does that is called the most general unifier. I'm not going to do it, but you can show that the most general unifier of two predicates is unique. And in this example, it's X into Y and Z into Mehmet. And if you plug Y into X and Z into Mehmet, okay, you'll get these two identical. And that's called the most general unifier.